Last time we were talking about non-homogeneous systems, and we did one example with that. And we're done basically with systems of differential equations. And today we will continue with higher order differential equations. Okay, let's talk about this. This is 4.1 in the book. And higher order linear ordinary differential equations. Linear ODEs. We'll talk about this. And using systems of equations, we will find the solution of higher order ODEs. Well, what's a higher order linear differential equation? Let's define this first. Definition. Well, we say, suppose you have a function of t, suppose that let y is a function of t, and nth order ODE, linear ODE, and nth order linear ordinary differential equation for y is of the form nth derivative of y, nth order ODE. So you have nth derivative in the equation plus a1 t, the coefficients are some functions of t, n minus 1 derivative here. And you continue like this. And finally, an t, the coefficient of y, okay, is equal to b of t. So when you have an equation in this form, you say it's an nth order linear ODE, okay? It's linear because we don't have any mixed term like y squared or t times y. We don't allow this in linear equation. And here, we only have single terms like y or t here, right? Function of t, they're fine. Well, if the right-hand side is 0, basically, if b is equal to 0, then you say the ODE is homogeneous. If b of t is equal to 0, then the ODE is homogeneous. Okay, so we will work with both homogeneous and non-homogeneous differential equations, like in the systems. Let's give an example here. Here's an example. third derivative of y with respect to t plus second derivative of y minus dy dt plus 5y is equal to 6t squared. It's a third order, is a third order linear non-homogeneous ODE. Okay. And the coefficients are constant. Here it's a constant coefficients ODE. Okay. Any question with this? Well, the question is, how do we solve this equation or something like this? Well, we convert this equation into a linear system. So let's talk about this now. Converting.
I'm so sorry. How do we know that it's non-homogeneous?
Because of this term here, 6t squared. Okay.
Okay, thank you.
Yeah. So when you have a function of t only in the equation, that makes the equation non-linear. Non-homogeneous. Okay.
Okay, thank you.
Yeah, good. Remember, homogeneous is used for different purposes. We also had this, right? dy dx or dt is equal to f y over t. That's another thing. Okay, so this is something else. It's also called homogeneous, but homogeneous is used for different purposes. Here, when we have a non-zero function on the right-hand side or non-zero function of a t, then you say it's a non-homogeneous system. This is also homogeneous, but this is something else. Okay, this one is here. We also say this is a homogeneous equation, but it's a different thing. Okay. Any other question?
Hocam dersle ilgili olmayan bir sorum vardı da.
Sor bakayım.
Hocam en son ben 13. dersi takip etmiştim de 14. derste miyiz?
Evet.
Teşekkür ederim.
Cuma günü tatil olduğu için yapamamıştık. Any other question, comment? All right, so let's convert a higher order ODE into first order system. We know how to solve first order systems. So we will convert this into first order system, and then using the methods of linear algebra, we will solve this higher order differential equation. Okay, so let's consider the equation ODE given by the following: y nth derivative. It's a linear ODE, a1 t n minus first derivative plus a n t y is equal to b of t. It's a non-homogeneous first order, nth order linear differential equation. Well, to get a system, so we will say, so we will have n functions, n different functions. So say x1, it's a function of t, x1t, okay? Let's say this is, for short, let's call it x1, okay? x1 is equal to y. So we will redefine our function y with x1, and let's say x2, it's again a function of t. I will not write again, but it's a function of t. Say x2 is the derivative of x1 prime, which is basically y prime, right? Because x1 is y. And x3 is x2 prime. Now, x2 prime is y double prime. Second derivative of y. And you continue like this. And finally, xn is xn minus 1. This is defined earlier, right? So it's the derivative of the previous one. And this is the n minus first derivative of y. Okay. So we introduce n functions, 1, 2, 3, right, up to n, x1, x2, x3, xn, and we will write a system for this here, for this ODE, okay? We will write a system for this one. Well, what is xn prime? Let's write x derivative of xn. Derivative of xn is basically derivative of y of order n, but derivative of y of order n is using the star by star. The nth derivative of y is minus a n t y. You take here this terms to the right hand side, okay? This is what we do to write nth derivative of y minus a n minus 1 t. These are functions, the coefficients, y prime. And you continue like that. Finally, minus a 1 t n minus first derivative of y plus b of t. Okay, plus b of t. Well, remember that y is x1, y prime is x2, and so you replace here this one with x1, and this is nothing but x2, okay? And this here is xn. So what you get from this, minus an t x1 minus a n minus 1 t x2, and you continue like this, minus a1 t xn plus b of t. Now we can write the system using this. Well, this tells you basically, let's rewrite all the derivatives. x1 prime, remember it was x2. It was given here, right? x1 prime, it's y prime, and y prime is equal to x2, okay? This here tells you that x1 prime is equal to x2. And similarly from here, x2 prime is x3. And you continue like this, okay? Let's write this here. x2 prime is equal to x3. Okay? And xn minus 1 prime is equal to xn. And what is the derivative of xn? Derivative of xn is here we write that, right? This one, okay? And this is a system, linear system. You can represent this as the following in a better way: x1, x2, xn. You take the derivative of this. It's equal to, you will have a matrix on the right-hand side, and this matrix is easy to write down. It's going to be, since we start with here x2, okay, the first row will be 0. For x2, we will have 1, 0, 0, okay? And next, we have here x3. That means the third entry will be 1 in the second row. 1, 0, and so on. You continue like that, okay? So basically, up to this one here, xn, we will have 0, 0, okay? And we will have ones here. One here, 0 here, okay? And the last one is the following. We use this one for the last row. It's going to be minus an. I will not write t here, but you will understand that it's a minus an t, minus an minus 1, okay? And you continue like this, and this is a1 minus a1. When you multiply this with x1, x2, xn, you will get the above system except for the non-homogeneous part, bt. So you will add 0, 0, and the last entry will be bt. Okay. Is it clear what we are doing? Okay, let me explain one more time.
Yeah, thank you.
So when you, let's go from here, the last part to the previous part. So when you multiply this matrix with this matrix, you take the first row and the first column to get the first entry, right? And this gives you what? X2, right? First row, first column gives you x2. So x1 prime here is equal to x2 plus 0, which is x2, and you get this one, okay? Next one. To get the next one, x2'nin yanında eksi olmayacak mı? Şuradan mı bahsediyorsunuz? Matrixin üzerinde. Yok. Şimdi açıklayayım, göreceksiniz. To get, for instance, to get this term here, okay? Yok, olmayacak. Şimdi göstereceğim. Tek tek. X2 prime, how do you obtain x2 prime? X2 prime is here, right? And you get x2 prime by multiplying this row with this column, okay? And you see that x2 prime is equal to x3, right? So where is x3 here? X3 is here. When you multiply this row with this column, you get x3 because the only non-zero term here is the third one, and you get 1 times x3, right? Right, this is 4.1, yes. Let's look at the last.
Hocam pardon, benim kastettiğim şeydi. Hemen matrixin üzerinde xn prime eşittir a eksi ant x1 eksi an eksi 1 t x2 yanındaki de eksi olmayacak mı?
Ha, şunu mu diyorsun? Tamam, şunu diyorsun. Şu.
Evet orası.
Tabii onlar eksi. Tamam, doğru. Tamam. All right. Well, look at the last one. Xn prime here. So we cover this line, Xn prime. So you take this row and this column, and this gives you, right, an minus an x1 minus an minus 1 x2 and so on, plus b of t. Okay, so we get the system. So this representation is important. Okay. Is it clear now? This is important, and we will here use this matrix a lot. This we will call it A. So basically, we get a system of linear non-homogeneous equation, right? All right. Well, let's do an example, and maybe we understand this better. And the purpose here is to find, remember, we will solve this for y. What is y? Y is x1. So you only need to find y, and it is x1. So you don't need to find all the functions here. Okay, you need to find one function, which is x1, because x1 is equal to y, okay? So the solution will be easier than the previous work, what we did for linear systems, okay? But the method will be similar. Let's do an example and write a linear system for this equation. The third derivative plus t times the second derivative of y minus t squared y prime plus 3y is equal to sine t. Well, this corresponds to the following. So let's say x1 is y and x2 is x1 prime, x3 is x2 prime. Okay, so you introduce three functions because it's a order 3 equation. Then this corresponds to, and maybe say x here, x1, x2, x3. So star is equivalent to, here, let's call it star here. Then star is equivalent x prime is equal to, the matrix will be 0, 1, 0, 0, 0, 1, and the last one will be, remember, minus 3 t square and minus t. So we use this coefficients, right? 3 here, this is an minus 1, an minus 2, and so on. Okay, to write down this row, right? And times x plus 0, 0, b of t is sine t. Is it clear? Any question?
Hocam, how we get the x1 equals y?
How do we get what? x1?
Equals y.
We choose like that. Yani böyle seçiyoruz. Hani x1 olarak y'yi seçiyoruz. x2 olarak x1'in türevini seçiyoruz. Sistem oluşturmak için bunu baştan böyle seçiyoruz.
Okay, thank you.
Yani bunu her zaman böyle yapıyoruz. We always choose x1 as y and x2 x1 derivative and so on. Okay. Later we will talk about the solution, but let's not go into that part now. So let's talk about the solution in the general case. That's right, yeah. So the structure of the solution set
Hocam o halde burada x2 y'nin birinci türevi olacak. Değil mi?
Duyamadım, bir daha tekrar eder misin?
Biraz derse geç kaldım da böyle yeni şey yapmaya çalışıyorum hocam. O yüzden
Tamam.
biraz böyle çok basic gelebilir. O zaman burada x2 y'nin birinci türevi.
X2 evet y'nin birinci türevi oluyor. Ama biz x2 ile ilgilenmiyoruz aslında. Sadece sistemi oluşturmak için kullandık. Çözerken y'yi bulmamız yetecek. Çünkü bilinmeyen y.
Çözerken y'yi bulacağız. Tamam.
Zaten y'yi bulduğun zaman x2'yi de x3'ü de bulmuş oluyorsun. Çünkü türev alarak bulabilirsin değil mi x2'yi?
Tamam.
Yani amaç burada y'yi bulmak. Yani x1'i bulmak.
Tamam hocam.
Tamam. Ama dediğim gibi evet öyle.
Tamam.
Güzel. Well, let's consider again nth order equation like this. A1 t y to the n minus 1, n minus first derivative, and a n t y is equal to 0. And this corresponds to the corresponding system, like in the previous example, is something like this. X prime is equal to ax plus, well, it's a homogeneous system, so let's talk about homogeneous first. X prime is equal to ax, right? Here a is, you know how to construct a now, but that's not important here. So let's say we have n solutions for this system. Let's call it star here. Okay. So say x1, these are vectors, okay? X2, maybe let's write like this. X1 t vector functions, x2 t x and t are linearly independent solutions. Linearly independent solutions of star, this linear system. In that case, maybe let me write here. What is x1? X1 is like this. X1 t, it's a vector function. So we have y1.
Pardon, bir şey sorabilir miyim?
Tabii.
Yukarıda starla belirlediğimiz equation'da ax plus b dememiz gerekmiyor mu acaba?
B yok çünkü bu 0 ya.
Ha, okey, pardon, tamam.
Homogeneous olduğu için burada yok.
Okey.
Önce homogeneous durumu inceleyeceğiz. Let's say these vector functions are the functions with coefficients like this, the vector with coefficients like this, y1, y. The second function is, remember, the derivative of the first function in the solution, y1 prime, y1 double prime, and so on. y1 n minus first derivative, it's, let's say, x1, okay? And let's say x n is the function, is the vector with this yn first derivative, yn second derivative, and so on. Yn n minus first derivative. All right, so these are the solutions of the system. In that case, it's easy to check that this y1 here, next one will be y2, and the final one will be yn. These are scalar functions, and they are linearly independent functions, okay? So It's maybe let me give this as an exercise for you. Y1, Yn are linearly independent solutions of the original nth order differential equation. Maybe let's call this double star here. Okay. Double star here, okay. So it's gonna be the solution, linearly independent solutions of double star, okay. So basically, when you find the solution, linearly independent solutions of the corresponding linear system, then you get a full set of solution for the nth order differential equation. Look at the first terms of each vector, first function of each vector. This will give you the required solutions, okay? That's the idea. Well, we will do examples later, but let's continue with 4.2 now. So this is about the homogeneous equations with constant coefficients. Equations with constant coefficients. Well, what is the question here? Maybe let's say show that these are linearly independent solutions, okay? Well, in this method, we will work with constant coefficients, otherwise it is not easy question. So we will consider basically something like this. An equation, nth order equation with constant coefficients means we will have constant here a1 for the n minus first derivative, and all other coefficients are constant a2, n minus 2 derivative, and you continue like this, an, y, and it's homogeneous. That means on the right hand side we have 0, where each coefficient is a real number, okay? So this is the simplest case, and we convert this into linear system. So it becomes basically, remember, x prime is equal to, maybe let's write it here like a times x, where what is a here? A is, remember, it was given by 0, 1, 0, 0, 0, 0, 1, 0, and you continue like this, 0, 0, 0, 1, 0, and finally we have minus an minus an minus 1 minus A1. Okay, we had this matrix for A. Well, what is the general solution for this system? Remember, the general solution is given by the fundamental matrix. And sometimes we use Jordan form or diagonalizable. If it is diagonalizable, it's easier, right? But anyway, and the general solution to the system is the following. We had x of t is equal to e to the, remember, exponential matrix, e to the at times a constant vector. This gives the general solution. And either diagonalizable matrices, or it may not be diagonalizable at all. So we use Jordan form, right? In that case, we use this form, P times e to the jt P inverse times the constant vector. What is P and J here? J is the Jordan block or Jordan's form, and P is the matrix with columns consisting of eigenvectors, right? So here, J is Jordan form of A, and remember A, P inverse is equal to J, okay? We had this. If it is diagonalizable, A is diagonalizable, then we have the similar equation, right? Instead of Jordan form, we have a diagonal matrix. But we have a shortcut here. The nice thing is, when you multiply P inverse with constant vector, you get another constant vector. So instead of writing this, we can write, since this is a constant vector, instead of this, we can write the following: P times e to the jt times another constant. Let's denote this constant by the same letter, C. Okay, this. Okay, this is easier to work because we don't need to compute the inverse of the matrix P here. Okay. Right, remember this from last time. Let's see what we get in simple cases like 2 by 2 here. When A is 2 by 2 matrix, okay, this is basically the case when we have second order differential equation. In that case, 2 by 2 case, A is what? A is a 2 by 2 matrix, 0, 1, minus A2, minus A1. And we will find the solutions in that case. To find the solutions of the system, we need to find the eigenvalues. To find the eigenvalues, we look at the determinant of A minus lambda I, okay, which is minus lambda here, 1 here, minus A2, minus A1 minus lambda, and the determinant becomes lambda square plus A1 lambda plus A2. Well, we get a nice polynomial of lambda, the coefficients of this polynomial, and A1 and A2. Okay, remember what is A1 and A2? A1 and A2, very from the beginning here, these are the coefficients. Okay, here this is A1, this is A2, and you see these terms when you try to find the eigenvalues. Okay. Well, the nice thing is this is not a coincidence. You can try 3x3 case. It's an exercise for you. Maybe let me write first the matrix. 0, 1, 0, 0, 0, 1, minus A3, minus A2, minus A1. This is A. And the determinant of A minus lambda I is, you can compute this yourself, minus lambda cube plus A1 lambda square plus A2 lambda plus A3. It's an exercise for you. Check this. Okay. Well, in general, again, this is like in the previous case, A1, A2, A3, and these are the coefficients of the original higher order ODE. And you can guess now, in the general case n by n, n by n case, A is, we already have it here, right? It's A, this. This is your A. And the determinant of, maybe, let me, okay.
Azıcık gidebilir misiniz?
Duyamadım, tekrar eder misin?
Hocam azıcık üste gidebilir misiniz?
İyi.
Teşekkür.
Well, this is going to be minus 1 to the n. This minus 1 to the n is not very important. And the rest is lambda to the n plus a1 lambda to the n minus 1 plus a n minus 1 lambda plus an. Okay. And we call this a characteristic equation of the system. Okay, so we will call this here. Let me define this. P of lambda, which is lambda to the n plus, without minus 1 to the n, it's not very important, as I said. because we will check the roots of this polynomial, and when you find the roots, -1 to the n will not have any role, right? A1 lambda to the n-1 and an-1 lambda plus an is equal to 0 is called the characteristic equation of the higher order ODE oops, sorry for this. Anyway, let me write this definition again. Definition. So we had this P of lambda, which is lambda to the n plus a1 lambda to the a-1 is equal to 0 is called the characteristic equation of the ODE above. Equation of ODE. Okay. So basically, to find the solutions of the system, you will use this characteristic equation, and we will go from that. Okay. Let's give a break here. Do you have any question, any comment? Yeah, we lost this part. All right, let's give a break until 11:45, 10 minutes. All right, let's continue. Do you have any question before we continue? All right, then let's do what? Well, let's consider different cases. The easiest case when we have different eigenvalues for the matrix, the associated matrix. So this is the case when we have distinct eigenvalues. So suppose that the characteristic equation P of lambda is equal to 0 has n distinct roots. Let's say these are lambda 1, lambda 2, and lambda n, okay? Then the matrix A is diagonalizable and the fundamental matrix in this case, remember, it's the exponential matrix, okay? Let's call it psi t is equal to P of P times e to the dt, which is this, e to the lambda 1 t 0 e to the lambda 2 t, and you go like this on the diagonal, e to the lambda n t, and all other entries are 0. Maybe let's put a big 0 here, or maybe let's write like this. Okay. And 0 here. Like that, okay? And the columns of this fundamental matrix will give you linearly independent solutions, right? So what is P here? P consists of eigenvectors, and lambda i's are eigenvalues of A. Here, P is the matrix consisting of eigenvectors v1, v2. Maybe let's write, okay. Yeah. Vn, and these are eigenvectors, okay? Of A, right? So what are the columns here? The columns are when you multiply So the general solution, right? The general solution to this system, x prime is equal to a times x, is, so these all we covered, we covered all these things in the previous week, right? So the general solution of the systems is basically the combinations of linear combinations of the columns of the fundamental matrix, or in short, you can write this as xt or x is equal to, maybe let's write this part first. X is equal to psi t times c. This gives you basically the linear combinations of columns, okay? And what is this? Well, remember here, psi is p times this e to the jt, and it's going to be like this. It's equal to, let's write it in the long way first. It's v1, v2, v3, vn times, this is p, times e to the lambda 1, e to the lambda n t, otherwise 0, okay, times the vector c, the constant vector c. Well, this is equal to what? Let's compute this matrix multiplication. This matrix multiplication will give you, take this as the first row and the first column here. It's going to give you e to the lambda 1 t times v1. And we also multiply with here c, so it's going to be c1 times e to the lambda 1 t times v1, the vector, okay, plus. Now you move to the second one, e to the lambda 2t. So basically you use the next one, e to the lambda 2t, and we have 0 here, and this, okay, 0 here. So we use this column and the same row. So this gives you c2 times e to the lambda 2t times v2. And you continue this process. Finally, you end up with cn e to the lambda n t times vn. Okay. Well, this tells you what? This tells you basically, remember this is x. What is x? X is the vector with this x1t, x2t, xn t, and we only need x1 because x1 is, remember we say x1 is equal to y. This is equal to y, and y is the solution of the original system. I do not have here, but it's the solution of nth order differential equation. So to obtain the first entry, what you have here is basically you have a combination of e to the lambda 1t, e to the lambda 2t, and so on. And this tells you basically, here v1, v2, these are constant vectors, right? These are eigenvectors, they're constant. So from this, you get that y is a combination of e to the lambda 1t, e to the lambda 2t, and so on. Maybe let's write it like this, c1 some other constant, because we don't know what v1, v2 are, right? Lambda 1t plus c2 tilde e to the lambda 2t plus cn tilde e to the lambda n t. Okay. Then this is the general solution. Of the ODE, linear nth order ODE, remember y nth derivative plus, how do you write this? A1 y to the n minus 1 plus an y is equal to 0. Okay, so we get a nice formula at the end to obtain a general solution of such a differential equation. Basically, you find the roots of the characteristic equation, and using these roots, we write the general solution. But remember, this is the case when we have different roots, different eigenvalues, basically. Repeated one, in the repeated case, we will do the similar thing, but the form of the solution will be a little bit different. We will talk about that as well. Let's do one example. The nice thing is here, remember, to solve this higher order differential equation, we write a linear system. We get the theory from linear system, but we don't, in practice, we don't need to use the methods of systems to solve higher order differential equations, okay? So we don't need to go with, this exponential matrix and so on. Because we only need one function, the first entry of the solution, and you can obtain the first entry by finding these eigenvalues. The eigenvalues will be enough to get, and you can get the eigenvalues using the characteristic equation. You don't even need to find the determinant, okay? Let me do an example and we will understand this better. So let us solve this equation, second order differential equation, linear differential equation. This is quite easy to solve, but let's do it with the characteristic equation. So what is the characteristic equation? P lambda is equal to lambda. It's a degree order 2 equation, so we will have degree 2 polynomial, lambda square minus 1, right, is equal to 0. That's it. The minus 1 comes from here, this one. Right? Then what are the roots? So this is the characteristic equation. Then the roots are lambda 1 is equal to 1, lambda 2 is equal to -1, and these are distinct, right? They are not the same. So when we have distinct roots, that means distinct eigenvalues, we write the solution as in the previous form, in the here red box. So the general solution is y of t is equal to e to the lambda 1 t, which is e to the t, and we have e to the lambda 2 t minus t, and you have the combination of this two, c1 plus c2, this, where c1, c2 are real numbers. All right. So you see here, we don't need to deal with the systems. We get the idea of the system, but in practice, we don't use the methods of systems when we solve higher order differential equations. Any question with this? Var mı soru arkadaşlar bununla ilgili? Anlaşıldı mı? Let's do another example. Solve y to the fourth derivative of y plus y is equal to 0. So this is again constant coefficient, higher order linear differential equation. To solve this, again we write characteristic equation. The characteristic equation it's lambda to the 4 plus 1 is equal to 0. Now the roots are, we don't have any real root here, but we have complex roots, right? So lambda to the 4 is equal to lambda to the 4 is equal to -1. How do you find the roots here? We use some basic complex algebra here. Well, it is, you can write e to the -1 is e to the I pi, okay? Maybe let me do this on the complex plane. This is -1. And it is e to the I pi. Pi is the angle. So when you make pi rotation here, you get -1. Okay. So it's e to the I pi. Well, so what are the roots here? What is lambda here? Well, the first root is lambda 1. Let's say lambda 1 is e to the I pi over 4, but we have 4 roots. It's a degree 4 equation, 4 polynomial. So we have 4 roots. One of them is the trivial one, e to the I pi over 4. E to the I pi over 4 is basically this complex number here. So what is this complex number? Basically, this is here pi over 4. Okay, so it's lambda 1. Well, the other complex root will be, you can find this by adding, maybe let's write here to find other roots. Rotate lambda 1 by 2 pi over, I will write here 4. What is this 4? This 4 comes from basically this one, okay? Okay, let me explain this here. Well, how do we get this e to the I pi? Maybe let me go over complex numbers. In general, when you have a number here, this is e to the I theta, okay? And this is theta, right? Angle. And -1 is here. This is -1 with length 1 here. -1 is here. So what is the angle here? The angle here is it's pi, okay? So that means this is equal to e to the I times theta. Theta is pi here, I pi, okay? For instance, this here, I, what is I in terms of e to the I something? What is I? What is the angle of I? The angle of I is pi over 2. So you can write I as e to the I pi over 2, like that, okay? Is it clear now? You look at the angle of the number. Well, -1, so this is -1, right? Or -1 is here. It follows from this. It's on the real axis, on the left-hand side, it's -1. So what is the angle of -1? Angle of -1 is pi. So you look at the angle from 0, right? So you always start from here and look at the angle. Angle from this to -1, it's pi. Oh, where do we get -1? It follows from this. Lambda 4 plus 1 is equal to 0. Yeah? It follows from the characteristic equation. All right. Okay, good. So is it clear what we are doing? Any question with this part? Did you understand how do we get the roots? So this is, in general, this is how we do, how we represent complex numbers in the polar form, basically. Okay, so we rotate lambda 1 by 2 pi over 4. So that means lambda 2 will be, so you rotate this, okay, by which angle here? This is pi over 2, or it is going to be 3 pi over 4. This is pi over 2. So in total, it is 3 pi over 4. And this point, lambda 2, is e to the 3 pi I over 4. Clear? So we get two roots. The other roots, you can continue with this process, or easier, you can take the conjugates. So maybe let's write here lambda 2. E to the 3 pi I over 4. Lambda 3 will be here. This is lambda 3. And lambda 4 will be here. But lambda 3 is basically the conjugate of lambda 2. Which is e to the minus 3 pi I over 4. And similarly, lambda 4 is conjugate of lambda 1, which is e to the minus I pi over 4. Okay, so we get 4 roots, and we can write the solutions corresponding to this 4 different roots, but these are complex roots. Remember, when we have the complex roots, real and imaginary parts will give you the solutions as well, so it's enough to consider 2 of them. So let's consider lambda 1 and lambda 2 to get the solutions. From lambda 1, we get solutions. Complex solutions, let's say. E to the lambda 1 t. What is this? E to the lambda 1 t. Maybe let's first write lambda 1 first. Okay, here. It's gonna be better. Well, what is lambda 1? Lambda 1 is e to the I pi over 4, which is cosine pi over 4 plus I sine pi over 4. And cosine pi over 4 is root 2 over 2 plus I times root 2 over 2. So e to the lambda 1 t is e to the root 2 over 2 plus I root 2 over 2 times t, which is basically e to the root 2 over 2 t times the imaginary part now, cosine root 2 over 2 t plus I times sine root 2 over 2 t, right? This is basically e to the I root 2 over 2 t. Okay, so this is the complex solution, one complex solution. From this, we have real part and imaginary part. You can write this as, let's continue this here, e to the root 2 over 2 t cosine root 2 over 2t plus I times e to the root 2 over 2t times sine root 2 over 2t. Okay, well, this is the real part. Let's call it x1t. And this is the imaginary part. Maybe let's call it real and imaginary part, otherwise it's going to be complicated. Real part and imaginary part. And they are both solutions, right? Real and imaginary parts are also solutions. So from one complex solution, you get two solutions, two real solutions, okay? And you do the same thing with the other root, lambda 2. E to the lambda 2t. Lambda 2t is, remember, lambda 2 is e to the 3 pi over 4. Maybe let's do this here first. Lambda 2 is e to the 3 pi I over 4, which is cosine 3 pi over 4. Cosine 3 pi over 4 is minus root 2 over 2 plus I times root 2 over 2. Okay, so this is lambda 2, and e to the lambda 2t is e to the minus root 2 over 2t times cosine root 2 over 2t plus I times sine root 2 over 2t, like in the previous case. And the real and imaginary parts are, again, let's write it, minus root 2 over 2t cosine root 2 over 2t plus I times e to the minus root 2 over 2t times sine root 2 over 2t. Well, this is again the real part. And here is the imaginary part. So you combine basically 4 solutions and you get the general solution now, okay? So the general solution y of t is, we take this one without I, okay? So let's copy this here. So C1 times this plus C2 times this, okay? Plus, we continue this and take this one. Real and imaginary parts again. C3, C4. Here C1, C2, C3, and C4, they are real numbers, okay? C1, C2, C3, and C4 are real numbers. All right, any question with this solution?
Hocam ilk kökün açısını nasıl bulmuştuk? Pi over 4'u.
Lambda üzeri 4 e üzeri ep ya.
Lambda'nın üzerinde hangi sayı varsa pi'yi ilk root olarak ona mı bölüyorum?
Evet, evet.
Tamam, sağ olun.
Diğerlerinde 2 pi bölü 4 kadar döndürerek bulduk. Ama zaten lambda 1 ve lambda 2 yeterli oldu. Lambda 3, lambda 4'ü bulduk ama kullanmadık. Gerek yok. Çünkü 2 tane farklı kompleks kökle 4 tane reel çözüm üretebiliyoruz. Zaten bu da 4. dereceden bir denklem yeterli oluyor.
Hocam 5 olsaydı nasıl yapacaktık? Fazladan bir tane conjugate part şey olmuyor mu?
Olamaz. 5 tane kompleks 5 tane kompleks kök
Lambda
olamaz.
üzeri 5 olsa?
O zaman bir tanesi reel olmak zorunda. Çünkü kompleks kök olduğu zaman onun konjugesi de kök olacak. Dolayısıyla kompleks kökler çift sayıdır.
Anladım.
O zaman reel olur. Reel için de ayrı bir çözüm yazacaksın. Onu da kombinasyona ekleyeceksin. There is one
Hocam
question. Can we choose eigenvalues freely? Yes, you can choose eigenvalues freely. There is no restriction on that part. Yes.
Hocam general solution yaparken i'leri silmemizin sebebi onların i'siz halinin aslında lambda 3 ve lambda 4 olması mı?
Bir daha söyler misin?
Bir saniye. Hocam general solution yazarken i'leri silmemizin sebebi aslında onların i'siz halinin lambda 3 ve lambda 4 olması mı?
İleri
Conjugate
silmemizin
olması mı?
sebebi çünkü kompleks kökü bulduk, kompleks çözümü bulduk. Kompleks çözümün reel ve imaginary partları reel çözümler oluyor. Reel çözümleri bulurken değil mi? Imaginary i'sız kısmını alıyoruz, i'siz kısmını alıyoruz. Çünkü reel demek i yok orada. Yani şöyle bir çözümüm varsa x1 t artı i y1t gibi bir şey varsa bu bir çözümse eğer şu bir çözüm, bu bir çözüm oluyor. Tamam mı?
Okay.
Bunlar reel çözümler oluyor. Tabii şeye dikkat etmek lazım. We have to be careful about choosing the roots. We could choose different roots, but when you choose different roots, be careful with the choice because if you choose this one with the conjugate, that will not work. The reason is they're not linearly, are they? Let me think about it. No, you can choose any roots you want. You can choose any two roots you want because anyway you will get linearly independent solutions. So you're free to choose any two different eigenvalues to work with. All right. Any other question, comment?
Hocam ben de şey sormak istedim. Böyle ilk başta dersin başında yaptıklarımızla bunların tam bağlantısını yani böyle burada yaptıklarımız sanki karakteristik equation ve sonrası.
Evet, karakteristik denklemin ya burada aslında bir önceki örnekten tek farkı burada kökler kompleks çıkıyor. Yoksa aynı örnek. Kökler kompleks çıktığı için kompleks çözümlerin reel ve imaginary partlarını alıp çözüm olarak onları yazıyoruz. Yine aynı durum. Karakteristik denklemin 4 tane farklı kökü var. Yani repeated root yok burada. Repeated eigenvalue yok. Dolayısıyla aynı yerdeyiz ama kökler kompleks, reel değil. Tek fark o.
Tamam hocam.
Aslında bunun benzerini kompleks köklerle ilgili daha önceki örnekte de yapmıştık. Orada da reel ve imaginary partları almıştık. Burada da aynı şeyi yaptık.
Evet, biraz böyle bu ama higher order falan o konuyu tam böyle ikisinin karşılaştırılmasını
Tabii,
yapsam
tabii.
güzel olur
Doğru.
böyle biraz
Evet,
birbirine
yani bu
geçmeye başladılar.
evet. Tabii bu evet doğru. Yani bu higher order ama yöntem aynı.
Evet, yöntem aynı. Tamam hocam, teşekkür ederim.
Any other question? Comment?
Hocam istediğiniz eigenvalue'ları alabilirsiniz dediniz ya, şeyi anlamadım. Yani, conjugate'den alınca iki tane aynı solution gelmiyor mu? Orayı ben tam çözemedim ya.
Bir bakayım. Ha tabii conjugate alınca tabii. Conjugate alınca yeterli şey olmuyor. Yani e, şu ikisini alamazsın doğru.
X1 ile
Yani,
X3'ü alamam değil mi? Conjugate oluyor.
X1 ile X3'ü alabilirsin ama X1 ile X4'ü alamazsın mesela. Bunlar birbirinin
Ha
conjugate.
onlar conjugate, tamam. Anladım.
Evet. You cannot choose this two to get the general solution because if you choose this two, you will get two solutions. You can check that. Okay, you will get two solutions, two real solutions, and this will not be enough to write the general solution. But you could choose the following. Instead of working lambda 1 and lambda 2, you could choose lambda 1 and lambda 3. Okay. Basically, if they're not conjugate to each other, you can work with the eigenvalues. Right, you cannot choose lambda 2 and lambda 3 because they are the conjugates of each other. The conjugates will give you the same roots, okay? Lambda 2 and lambda 3 will give you the same solutions. So this will not enough to write the general solution.
Hocam kompleks deyince imaginary part böyle şey değiştiriyor, işaret değiştiriyor. Burada da o zaman x ekseni real kısım, y ekseni de böyle i'li kısım.
Evet. Burası real z,
Tamam,
and this is imaginary z, right?
tamam, teşekkür ederim.
Imaginary z. So this, if you say this is a plus bi, this is a minus bi, okay? Or if you say this is e to the I pi over 4, this is e to the minus I pi over 4. You can write it like this as well, okay? Oldu mu? Question, comment? Now we'll stop here. So next time we'll continue with more examples with higher order equations. We'll also talk about the non-homogeneous equations, and this is about the method of undeterminate coefficients. There are many ways to deal with non-homogeneous higher order equations, and we'll talk about those, okay? All right, see you on Friday. Bye.
İyi günler hocam.
Thank you hocam, iyi günler.
Geçebilir misiniz
Görüşürüz.
biraz?
Hı hı. İyi mi böyle?
Evet, çok teşekkür ederim. Bir saniye.
Evet.
Çok teşekkürler hocam. İyi günler.
Görüşürüz, iyi günler.